Consider the rock in your hand, a paragon of stillness. It rests, heavy and inert, a symbol of permanence. Or perhaps gaze into a tranquil cup of tea, its surface a placid mirror. We perceive these things as static, as anchors in a fleeting world. But this perception, this comforting illusion of stability, is perhaps the most profound deception our senses have ever crafted. For if we could attune our eyes to the true nature of reality, we would discover that the universe permits no such thing as absolute rest. Nothing, from the smallest conceivable constituent of matter to the grandest supercluster of galaxies, ever truly stands still. Existence is a symphony of ceaseless motion, an intricate, unending dance choreographed by the fundamental laws of physics. To understand this universal dynamism is to embark on a journey, a voyage that will take us from the frenetic heart of the atom to the unfathomable, expanding frontiers of the cosmos itself. Our journey begins not by looking out, but by looking in. Let us descend into the seemingly placid world of that teacup. What appears as a serene pool is, in reality, a maelstrom of activity. The water molecules, each a tiny trio of atoms, are in a state of wild, unrelenting commotion. They vibrate, rotate, and collide with unimaginable frequency, billions of times every second, driven by the thermal energy they possess. This is the hidden world revealed by the phenomenon of Brownian motion. In 1827, the botanist Robert Brown, peering through his microscope, observed pollen grains suspended in water. He expected them to be stationary, but instead they jittered and danced. They moved erratically, with no apparent cause. For decades, this was a baffling curiosity, a ghost in the machine of classical physics. It was not until 1905, in his miracle year, that a young Albert Einstein provided the definitive explanation. He theorized that the visible pollen grains were being jostled, pummeled from all sides by the invisible, hyperactive water molecules. Imagine a colossal beach ball being pushed and shoved by a crowd of thousands, each person pushing in a random direction. The ball would tremble and wander, its path a testament to the chaotic energy of the unseen multitude. This is the reality within every drop of water, every lungful of air, every solid object we perceive as motionless. It is a perpetual, microscopic storm, a fundamental kinetic reality that underpins the very concept of temperature. The warmer an object is, the more violent the internal pandemonium. Only at the theoretical and ultimately unattainable point of absolute zero would this molecular agitation finally cease. But our universe, even in its coldest voids, is never truly that cold. The background hum of creation, the faint afterglow of the Big Bang, ensures that a baseline of energy always remains, keeping this microscopic dance alive everywhere, always. But even this frenetic ballet of molecules is not the bottom floor of reality. We must plunge deeper still, into the atom itself. For generations, we envisioned the atom as a miniature solar system, a dense nucleus of protons and neutrons with electrons orbiting like dutiful planets. This is a clean, orderly, and deeply misleading picture. The quantum revolution of the early 20th century shattered this classical model. The electron is not a tiny sphere following a predictable path. According to the principles of quantum mechanics, its existence is far more ethereal. The Heisenberg Uncertainty Principle, one of the cornerstones of this new physics, dictates a fundamental trade-off in the universe. It states that we can never simultaneously know with perfect accuracy both the position and the momentum of a particle like an electron. The more precisely we pinpoint its location, the less we know about its velocity, and vice versa. This isn't a limitation of our instruments. It is an intrinsic property of nature. The electron, therefore, cannot be a static point. To be perfectly still, its momentum would have to be precisely zero, which would mean its position would be infinitely uncertain. It would, in essence, be everywhere at once. Instead, the electron exists as a probability cloud, a haze of potential locations, surrounding the atomic nucleus. It is a smear of existence, a ghost that is constantly in a state of flux, its presence a shimmering probabilistic dance. It is never at rest. Its very identity is woven from the fabric of motion. To halt an electron would be to violate the fundamental grammar of reality, and the quantum weirdness does not stop there. If we could somehow magnify a patch of what we call empty space, zooming down past the scale of atoms and their constituents, we would find that it is not empty at all. The vacuum of spacetime is a seething, effervescent cauldron of activity. It is known as the quantum foam. Here, for fleeting, impossibly brief moments, pairs of virtual particles, an electron and its antimatter twin, a positron, or a quark and an antiquark spontaneously erupt into existence. They borrow a sliver of energy from the universe itself, permitted by a time-sensitive loophole in the laws of conservation. They exist for an instant, shorter than a trillionth of a second, before annihilating each other, repaying their energy debt and disappearing. This is happening everywhere, at every moment. The void itself is alive with a ceaseless churn of creation and destruction. Absolute nothingness, a state of perfect stasis, is a physical impossibility. The universe, even in its most vacant corners, refuses to be still. It is a restless ocean of potential, constantly bubbling with transient life. The very fabric of spacetime is a dynamic, energetic entity, a far cry from the passive, empty stage envisioned by earlier physics. The stillness we crave is a fiction. The universe is fundamentally, irreducibly, and beautifully restless. Now, let us pull our perspective back, rising from the subatomic chaos. We return to ourselves, standing on the surface of the earth. We feel the ground solid beneath our feet, the epitome of stability. Yet this sensation is a profound illusion, born of our shared frame of reference. We are all passengers on a colossal spacecraft, and its movements are so smooth, so vast, that we do not perceive them. First, there is the rotation of our planet. At the equator, the surface of the Earth is spinning at a dizzying speed, moving at over 1,600 kilometers per hour, or about 460 meters per second. Even as you sit seemingly at rest, you are hurtling through space faster than a rifle bullet. This relentless spin gives us our cycle of day and night, a daily testament to a motion we cannot directly feel. This was a truth for which figures like Galileo Galilei risked everything. The prevailing view, inherited from Ptolemy and sanctified by the Church, was that Earth was the unmoving center of all creation. To suggest otherwise was heresy. But the evidence of the heavens, of the moons of Jupiter, and the phases of Venus was undeniable. The Earth was not static, it was in motion. And this planetary pirouette is merely the beginning of our cosmic journey. As it spins, our world is also careening through space in its annual orbit, around the Sunday. To maintain this orbit against the Sun's immense gravitational pull, the Earth must travel at an astonishing velocity of approximately 30 kilometers per second. That's over 100,000 kilometers per hour. Every minute, we traverse a distance of nearly 1,800 kilometers along our orbital path. Think of it this way. During the time it takes to brew a cup of coffee, you have traveled a distance greater than the width of a continent. All of humanity, our history, our triumphs and tragedies, are being carried through the void on a rock moving at this incredible pace. We are all cosmic voyagers, locked in a gravitational dance with our star. The complex interplay of gravity and inertia, first mathematically described by Isaac Newton, dictates this perpetual transit. An object in motion stays in motion unless acted upon by an external force. In the near vacuum of space, there is virtually no friction to slow the Earth down, and so it falls endlessly around the Sun, its forward momentum perfectly balanced with the Sun's gravitational embrace, creating the stable, life-giving orbit we depend upon. Stillness is not an option. To stop moving would be to cease falling sideways, and instead plummet directly into the fiery heart of our star. But even our magnificent Sun, the anchor of our solar system, is not a fixed point in the cosmos. It too is a traveler on a far grander journey. Our entire solar system, a family of planets, moons, asteroids, and comets, is embedded within one of the spiral arms of a vast stellar island we call the Milky Way galaxy, and this entire celestial structure is in motion. The Sun, dragging the Earth and all its siblings along with it, is orbiting the supermassive black hole at the galactic center. This is a voyage of truly mind-boggling scale. Our speed on this galactic circuit is a staggering 220 kilometers per second. That's nearly 800,000 kilometers per hour. Even at this extraordinary velocity, a single orbit around the galaxy, a galactic year, takes our solar system roughly 230 million Earth years to complete. The last time our planet was in this same region of the Milky Way, dinosaurs were just beginning to roam its surface. The entire history of the human species has unfolded during a tiny fraction of this single, sweeping journey around our galaxy. When astronomers in the 20th century, like Vera Rubin, began to meticulously measure the rotational speeds of galaxies, they encountered a profound mystery. The stars on the outer edges were moving far too quickly. According to our understanding of gravity and the visible matter in the galaxy, these outlying stars should have been flung off into intergalactic space, like water from a spinning wheel. The fact that they were not implied there was a tremendous amount of unseen mass, a gravitational glue holding the galaxy together. This was the first compelling evidence for what we now call dark matter. This mysterious, invisible substance, which does not emit or interact with light, is thought to make up about 85% of the matter in the universe. Our galaxy's majestic, rapid rotation is a direct consequence of this unseen halo, another layer of cosmic activity driven by a substance we cannot even perceive. The Milky Way's very structure is a dynamic testament to this invisible influence. The story of our motion, however, does not end at the galactic border. Even our entire galaxy, this swirling metropolis of 200 billion stars, is itself hurtling through the void. It is a member of a small collection of galaxies known as the local group, and within this group, we are on a collision course. The nearest major galaxy to our own, the Great Andromeda galaxy, is currently about 2.5 million light-years away, but that distance is shrinking. Pulled together by the relentless force of mutual gravity, the Milky Way and Andromeda are converging at a speed of about 110 kilometers per second. Visualizing this requires a profound leap of imagination. Two colossal islands of stars, each containing hundreds of billions of suns, each spanning over 100,000 light-years, are falling toward one another across the chasm of intergalactic space. In about 4.5 billion years, they will begin to merge. This will be a cataclysmic, yet strangely delicate, dance. The galaxies will pass through one another, their shapes distorted by tidal forces, while direct collisions between individual stars will be exceedingly rare. Due to the immense distances between them, the gravitational disruption will be monumental. Great streams of stars and gas will be thrown out into long tails, and the star formation rate will skyrocket as gas clouds are compressed. Over hundreds of millions of years, the two galaxies will coalesce into a single, larger elliptical galaxy, a process some astronomers have playfully dubbed the birth of Milkomeda. This future cosmic smash-up is one of the most dramatic examples of motion on a grand scale, a gravitational destiny set in motion billions of years ago. Yet, even this galactic collision is just a local event, a detail in a much larger picture. For there is one final layer of motion, the most profound of all. It is the motion of space-time itself. In the 1920s, astronomer Edwin Hubble made a discovery that fundamentally reshaped our entire understanding of the cosmos. Using the powerful Hooker telescope at Mount Wilson Observatory, he observed that distant galaxies were not static in the sky. Almost all of them were moving away from us. And more startlingly, the farther away a galaxy was, the faster it appeared to be receding. This was the first observational evidence for the expansion of the universe. This is not motion times through time-space in the conventional sense, like galaxies flying away from a central point. It is the very fabric of space-time itself that is stretching, carrying the galaxies along with it. The most common analogy is that of raisins in a rising loaf of bread. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be receding. There is no center to this expansion. It is happening everywhere. This universal inflation is the enduring legacy of the Big Bang. Some 13.8 billion years ago, the entire observable universe was compressed into a point of unimaginable density and temperature. From that singular moment, it has been expanding and cooling ever since. The initial impetus of that primordial explosion set everything in motion, a cosmic shockwave that continues to propagate today. Every particle, every star, every galaxy carries within it the kinetic inheritance of that first cataclysmic instant. The reason nothing stands still is because the universe itself began in the most dynamic state imaginable, and its fundamental nature is one of expansion. The space between galaxies is not an empty void. It is an active, growing medium. This is the ultimate source of universal unrest. To be at rest in our universe is impossible, because the stage itself is in motion. This cosmic expansion is inextricably linked to the flow of time itself. The second law of thermodynamics, one of the most fundamental principles in physics, describes a property called entropy, which is essentially a measure of disorder or randomness. The law states that in an isolated system, entropy can only increase over time. A tidy, ordered room will naturally become messy. A hot cup of coffee will cool as its concentrated thermal energy dissipates into the surrounding cooler air. The universe as a whole behaves as such a system. It began in a state of incredibly low entropy, highly ordered and concentrated. And ever since the Big Bang, it has been on a one-way journey toward a state of maximum entropy, or heat death, where all energy is evenly distributed and no useful work can be done. This inexorable increase in disorder is what gives time its arrow. It is why we remember the past but not the future. The constant motion we observe everywhere, from colliding molecules to receding galaxies, is a physical manifestation of this process. It is the universe relentlessly exploring new, more disordered configurations. Motion is the mechanism of entropy's increase. A universe that was perfectly still would be a universe where time had no meaning, a universe frozen in a state of unchanging, maximum order, a possibility that the initial conditions of the Big Bang and the laws of physics seem to forbid. The constant flux we witness is the universe living, breathing, and aging. Albert Einstein, with his theory of general relativity, gave us an even deeper way to understand this relationship between matter, space, and motion. He revealed that space and time are not separate entities, but are woven together into a single, four-dimensional fabric, space-time. He also showed that this fabric is not passive or flat. It is warped and curved by the presence of mass and energy. Imagine a stretched rubber sheet. Placing a heavy bowling ball in the center will create a deep depression. A smaller marble rolled nearby will not travel in a straight line. It will follow the curve in the sheet created by the bowling ball. This is Einstein's vision of gravity. It is not a mysterious force acting at a distance, but a consequence of the geometry of space-time. Planets orbit the Sun not because they are being pulled by an invisible tether, but because they are following the straightest possible path through the curved space-time created by the Sun's immense mass. In this context, motion is the natural state of being. An object simply follows the contours, the geodesics, of space-time. To be still in a gravitational field would require a constant application of force, like a rocket firing its engines to hover above a planet. The ground beneath our feet is constantly pushing up on us, preventing us from following the natural, curved path toward the Earth's center. In a very real sense, the feeling of being stationary is the feeling of having our natural motion through space-time obstructed. The true state of rest, or free fall, is one of motion as experienced by an astronaut floating weightlessly in orbit. They are simply following the path of least resistance through the cosmic landscape, Einstein's masterpiece reveals that motion is not something that happens times within times, space-time. Motion is an intrinsic property of time space-time itself, the inevitable response of matter to the very shape of reality. So, we are left with a staggering and beautiful conclusion. The stillness we perceive is a localized, fleeting illusion, a trick of perspective. We are adrift in a universe defined by flux. We are composed of atoms whose electrons exist as clouds of ceaseless probability. These atoms form molecules that are locked in a violent, thermal dance. We stand on a planet that spins on its axis while hurtling around a star. This star, in turn, journeys around a galactic core at an incredible speed. Our galaxy itself is falling toward its neighbor, setting the stage for a cosmic merger of epic proportions. And all of this is happening within a universe whose very fabric is stretching, carrying everything along for the ride, a legacy of its explosive birth. From the quantum foam to the cosmic web, there is no escape from this dynamism. It is the core truth of our physical existence. This raises profound philosophical questions. If everything is in constant motion relative to everything else, what does it mean to have a location? What does it mean to be here? Our position is only ever meaningful in relation to another moving object. Our sense of place is a transient, relational concept in a cosmos, where there are no fixed coordinates, no absolute grid. We are all just patterns of energy, temporarily coherent structures, persisting for a brief cosmic moment as we are swept along in the universal current. This can feel disorienting, a loss of the anchor we call home, but it can also be liberating. It connects us to everything else in the universe. The motion in our blood is powered by the same thermodynamic laws that drive the expansion of the cosmos. The atoms in our bodies were forged in the hearts of stars that traveled for eons across our galaxy. We are not separate from the universe. Looking in, we are a part of its unfolding, a piece of its grand, kinetic story. The universal absence of stillness is not a flaw or a chaotic accident. It is the engine of creation, the source of change, complexity, and life itself. A static universe would be a dead universe, a place with no potential, no future. Our restless cosmos is a cosmos of possibility. It is a place where stars can form, where planets can coalesce, where life can emerge and contemplate the very motion from which it was born. The next time you hold a stone in your hand or gaze into a silent pool of water, remember the hidden universes of activity within. Remember that you are a passenger on a cosmic vessel, participating in a journey of unimaginable speed and scale. Embrace the flux, for in the unceasing motion of all things, we find the deep, vibrant, and undeniable pulse of reality itself. The universe never stands still because to do so would be to cease to be. What if the most profound act of creation in the universe, the birth of a star, was not a gentle awakening but a cataclysm of unimaginable violence? We are conditioned to think of the cosmos as a place of serene silent majesty, a vast and patient cathedral where light travels for eons across an ocean of tranquil darkness. We look to our own celestial home, the Milky Way, and we find evidence that supports this comforting vision. Here in our quiet, spiral-arm star birth is a slow, deliberate, and almost sacred process unfolding on timescales that defy human comprehension. Imagine a colossal, invisible river flowing through our galaxy. This river is not made of water, but of hydrogen and helium gas, unimaginably cold and diffuse. It meanders through the interstellar void, swirling into ethereal eddies and forming deep, dark reservoirs of potential. These are the molecular clouds, the stellar nurseries of the Milky Way, places like the Great Nebula in Orion, or the pillars of the Carina Nebula. Within these cosmic wombs, gravity, the universe's most patient sculptor, begins its work. It doesn't rush. It coaxes, it gently persuades. Over millions upon millions of years, the invisible hand of gravity nudges these sparse atoms closer together. It gathers wisps of dust and gas, weaving them into denser and denser knots, compressing these pockets of chilling cold until they begin to warm from within. A protostar, the embryonic heart of a future sun, begins to glow faintly shrouded in its natal cocoon. It is a process of slow accumulation, a celestial gestation period that can last 10 million years, a span of time in which entire species can rise and fall on our own world. The final result is a stable, long-lived star, a new point of light joining a cosmic dance that is measured and graceful. Our galaxy produces on average just a handful of these new suns each year. Perhaps 3 or 4. It's a sustainable, almost ecological rhythm, a galaxy carefully managing its resources of gas, ensuring a legacy of light for billions of years to come. The Milky Way is a cosmic gardener planting seeds with meticulous care, tending a stellar garden that blooms in slow, predictable cycles. This is our baseline. This is our understanding of how the universe builds itself one sun at a time, a process defined by patience and persistence. But this quiet story of creation, this gentle narrative of birth, is not the only one the universe tells. It is not even the most common. It is simply our story, the one we see from our privileged, peaceful vantage point. Out there in the deepest chasms of intergalactic space, across distances so profound, they challenge the very meaning of location. A radically different and terrifyingly violent drama is unfolding. When we turn our most powerful telescopes toward these distant realms, the serene portrait of the cosmos is shattered, replaced by a vision of chaos, frenzy, and overwhelming power. We see galaxies that are not calm, stately spirals, but twisted, mangled wrecks of cosmic collisions. We see galactic cores that are not gentle beacons, but blindingly brilliant furnaces spewing out energy on a scale that dwarfs entire civilizations of stars. They blaze in the infrared, their light screaming across the electromagnetic spectrum, a heat haze signature of something furious and hidden, taking place deep within their dust-choked interiors. These are not gardens. These are foundries operating at a breakneck, impossible pace. They are cosmic engines running so hot they threaten to tear themselves apart. We call them starburst galaxies. The name is deceptively simple, yet it describes one of the most extreme phenomena in the known universe. A starburst is not merely an increase in star formation, it is a paradigm shift. It is the difference between a campfire and a global firestorm. It is a runaway, galaxy-wide chain reaction of birth and death on a scale that is difficult to put into words. Where our Milky Way calmly produces a few stars a year, a typical starburst galaxy forges hundreds. The most extreme among them, the true monsters of the cosmos, can ignite 1,000 new suns in that same period of time. Let that number settle in. 1,000 new stars every single year. It is a rate of production so frantic, so far beyond our local experience, that it forces you to reconsider the fundamental physics of a galaxy. It means that in the time it takes for you to watch this film, a galaxy 1 billion light-years away could have given birth to a cluster of brilliant massive suns, each one larger and brighter than our own. It is a torrent of creation, a flood of light and energy that reshapes the very chemistry and structure of its environment. Entire generations of stars are born in the geological blink of an eye. These are the universe's most violent star factories, and what they are manufacturing transforms everything around them. This is not the slow, patient process we witness in our own cosmic backyard. There is no gentle persuasion from gravity here. Instead, starbursts are fueled by shock waves, by the brutal compression of gas on an unimaginable scale. Imagine 2 galaxies each containing hundreds of billions of stars and immense reservoirs of cold hydrogen gas, locked in a gravitational death spiral. For millions of years they dance around each other, their immense gravities raising colossal tides of stars and gas stretching and distorting one another like cosmic clay. Then they collide. It is not a collision of solid objects, but an interpenetration of entire star systems. The stars themselves, being so far apart, rarely hit one another. But the vast diffuse clouds of gas that permeate each galaxy have no such luxury. They slam into each other at millions of miles an hour. The impact creates shock waves that ripple through the colliding clouds, compressing the gas with incredible violence and efficiency. Trillions of tons of hydrogen are crushed into impossibly small spaces, triggering a firestorm of star formation all at once across tens of thousands of light-years. The result is a celestial crucible. In the dense, chaotic heart of this merger, protostars don't form in quiet isolation over millions of years. They are forged in crowded, turbulent clusters, competing for material in a violent gravitational mosh pit. The sheer density of available fuel means that the stars born in these firestorms are not like the typical stars in our galaxy. The process disproportionately favours the creation of behemoths, brilliant blue-white giant stars that are dozens or even 100 times more massive than our Sun. These are the rock stars of the cosmos. They burn with an incandescent fury blazing through their nuclear fuel in a mere fraction of the time our own Sun will exist. They live fast and they die young, and their deaths are as spectacular as their births. After only a few million years, these massive stars explode as supernova cataclysmic detonations that outshine the entire galaxy for a few brief glorious weeks. Each supernova sends a new powerful shockwave ripping through the surrounding gas, compressing it further, and in a violent feedback loop triggering yet another furious round of starbirth. A starburst galaxy is a system at war with itself, a place where the cradle of creation is also the scene of its own destruction. The very process that gives birth to its stars also creates the seeds of their demise. The relentless supernovae, the ferocious stellar winds from the massive newborn suns, all this energy begins to blow the remaining gas right out of the galaxy. A starburst can be so violent, so overwhelmingly powerful, that it can effectively sterilize its own galactic home, consuming or expelling all of its raw fuel for future generations in a brief, brilliant flash of cosmic history. It is a story of boom and bust written on the grandest of all possible scales. Why should we care about such distant, violent events? Because in these cosmic forges, the story of our own existence is being written. The early universe was composed almost exclusively of hydrogen and helium, the simplest elements forged in the Big Bang. Every other element, every complex atom that makes up our world and our bodies, the carbon in our cells, the oxygen, we breathe, the iron in our blood, had to be created. They were all synthesized in the nuclear hearts of stars and blasted out into the cosmos when those stars died. Starburst galaxies are the universe's high-yield chemical factories. By producing so many massive stars so quickly, and then ensuring those stars explode as supernovae in short order, they enrich the interstellar medium with heavy elements at a ferocious rate. They are seeding the cosmos with the raw materials for future planets, for complexity, for life. The violent processes we witness in these distant galaxies are a crucial part of the cosmic supply chain that ultimately led to the formation of our Earth and to us. We are in a very real sense the children of these ancient cosmic firestorms. To understand our own origins, we must therefore understand these extreme environments. We must journey into the heart of these galactic tempests. We have to become cosmic detectives, piecing together the evidence from light that has travelled for billions of years to reach us. We must decipher the gravitational language of chaos, trace the ghostly trails of galactic mergers, and peer through impenetrable veils of dust to witness the violent birth of stars. Our journey into these celestial infernos, these ultimate crucibles of creation, has only just begun. What we find there will not only reveal the secrets of the most extreme objects in the universe, it will tell us more about the intricate, violent, and beautiful story of how we came to be. What if the universe's most profound act of creation wasn't a gentle, patient process? What if it was a firestorm, a cataclysm of such unimaginable fury that it could forge 1,000 solar systems in the blink of a cosmic eye? We are taught to see creation as a delicate art, a slow dance of matter and energy, and for the most part, in our quiet corner of the cosmos, this holds true. To understand the violence that awaits us, we must first appreciate the peace. We must journey into the tranquil heart of our own galaxy, the Milky Way, into the places where stars are born not in a frantic rush, but with a deep gravitational patience. Look here at the sweeping arms of a spiral galaxy like our own. These are not merely static rivers of light. They are dynamic churning structures. They are cosmic traffic jams, density waves that sweep through the galactic disk, compressing the thin, cold gas and dust that drifts between the stars. This interstellar medium, a phantom fog of hydrogen, helium, and trace elements, is the raw material of creation. For billions of years, it can float in near-perfect equilibrium, a state of serene balance between the inward pull of its own gravity and the outward push of its internal energy. It is a cosmic ocean, vast and undisturbed. But within the spiral arms, the equilibrium is shattered. the compression wave acts like a celestial hand gently squeezing these diffuse clouds. As the gas and dust particles are crowded together, gravity, the universe's great sculptor, begins to assert its dominance. Whispers of attraction become shouts. Vast, dark nebulae, hundreds of light years across, begin to collapse under their own immense weight. These are the molecular clouds, the stellar nurseries of the galaxy. They are frigid places barely 10 degrees above absolute zero, so cold that molecules can form and persist, cloaking the cloud in an opaque shroud. Inside this chilling darkness, the process of birth accelerates yet remains astonishingly slow. Gravity is relentless but not instantaneous. Over hundreds of thousands of years, the cloud fragments into smaller, denser clumps. Each clump is a gravitational seed, a potential solar system in the making. Imagine you are shrinking down, plunging into one of these dark, chaotic cocoons. The void around you is not empty. It is a maelstrom of swirling gas and dust, all spiraling inward toward a common center. This is a gravitational vortex, and at its heart, a protostar is taking shape. The infalling material doesn't simply crash into the center. Conservation of angular momentum, the same principle that makes a spinning skater speed up when they pull in their arms, forces the material into a flattened rotating structure. This is the protoplanetary disk, a spinning platter of gas and dust from which future planets will one day coalesce. It is a chaotic, beautiful mess, a celestial potter's wheel, shaping the raw clay of the cosmos. At the very center of this disk, the core of the protostar grows ever denser, ever hotter. The pressure from the sheer weight of accumulating matter becomes unimaginable. Atoms of hydrogen are stripped of their electrons and crushed together with a force that defies comprehension. For millennia, the protostar glows not from nuclear fire, but from the heat of this intense compression. It is a cosmic ember radiating away the energy of its own collapse. But it is not yet a true star. It hasn't yet ignited its own engine. The final step is the most dramatic. The core temperature climbs, pushing past 1 million degrees, then 5, then 10. Finally, it reaches the magic number around 15 million degrees Celsius. At this critical threshold, the electrostatic repulsion that keeps hydrogen nuclei apart is finally overcome by the sheer violence of the pressure. Protons fuse. In a single transcendent moment, nuclear fusion begins. The protostar awakens, unleashing a torrent of energy that pushes back against the relentless crush of gravity. A star is born. Its light, its stellar wind, blasts away the remaining shroud of gas and dust, revealing the newborn sun to the universe for the very first time. This process from diffuse cloud to burning star can take millions of years. It is a stately, almost leisurely affair. In a typical spiral galaxy like our own Milky Way, this delicate ballet of gravity and pressure produces on average just a few new stars per year. It is a sustainable, gentle cycle of cosmic renewal, a slow and steady heartbeat that has kept our galaxy alive and vibrant for over 13 billion years. This is the universe as we know it. Calm, measured, patient. But the universe has a secret. A violent, spectacular and terrifying secret. Out in the dark, in galaxies both near and unimaginably far, there are places where this gentle process has been thrown into absolute chaos. Places where the calm rhythm of starbirth has been replaced by a raging galaxy-scale conflagration. What if you took the star formation of an entire galaxy like the Milky Way, all its countless stellar nurseries, and compressed that activity into a space just a few thousand light years across? What if you dialed up the rate of creation not by a factor of 10 or even 100, but by 1,000 or more? You would get something that defies the placid astronomy of our own galactic neighbourhood. You would get a starburst. These are not simply galaxies that are a bit more active. They represent a completely different mode of cosmic evolution, a brief frenetic period of creation so intense it can reshape the destiny of an entire galaxy. To an optical telescope, a starburst galaxy might not look like much. In fact, many of them appear frustratingly dim, shrouded, and unassuming. The very thing that fuels their fire is also what hides them from our view. Starbursts are choked with unimaginable quantities of gas and dust, the raw fuel for their stellar factories. This cosmic dust acts like a thick, impenetrable fog, absorbing the brilliant blue and white light of the tens of millions of young, massive stars being born within. If you could somehow peel back this veil, you would be blinded. You would witness a scene of celestial pandemonium, not just a few stellar nurseries, but a whole city of them packed shoulder to shoulder, clusters of brilliant, massive blue stars, each one hundreds of thousands of times brighter than our sun blaze with a ferocious light. But these stars are ephemeral. Their immense brilliance comes at a cost. They burn through their nuclear fuel in just a few million years, a fraction of our sun's 10 billion year lifespan. They live fast and die young, ending their lives in the titanic explosions we call supernovae. And in a starburst galaxy, these explosions are not rare, isolated events. They are a constant percussive drumbeat. A supernova might go off every few weeks or even more frequently. Each blast sends devastating shockwaves ripping through the surrounding gas, compressing it further, and triggering yet another furious wave of star formation. It's a chain reaction of cosmic proportions. Birth triggers death, and death triggers birth, a self-perpetuating cycle of creation and destruction on a scale that is difficult for the human mind to grasp. The entire core of the galaxy becomes a pressure cooker, a celestial engine running so hot and so fast that it seems it must tear itself apart. So if we can't see this incredible light show directly, how do we know it's happening? We must look at the universe through different eyes. While the dust curtain blocks visible light, it cannot contain the sheer energy of the starburst. The dust grains absorb the fierce ultraviolet radiation from the millions of young stars, and in doing so they heat up like asphalt on a summer day. And just like any warm object, they radiate that heat away. But they do so not in visible light, but in the infrared part of the spectrum. A starburst galaxy doesn't just glow in the infrared, it screams. It is one of the most luminous objects in the entire universe, pouring out 100 or even 1,000 times more energy than the Milky Way. And almost all of that energy, up to 99% of it, emerges as a colossal flood of infrared radiation. For astronomers, this is the telltale signature, the fingerprint of a monster. When we point our infrared telescopes at the sky, these galaxies blaze forth, outshining everything around them. They are celestial blast furnaces hidden behind a veil of their own fuel, but betrayed by their own incandescent heat. The story of their discovery is a testament to how profoundly our view of the cosmos can change when we learn to see a new kind of light. For much of the 20th century, astronomy was a science of the visible. We studied the universe through optical telescopes capturing the same kind of light our eyes can see. And in that light, the universe seemed to be a relatively orderly place. Galaxies were island universes, pinwheels of stars and gas evolving slowly over eons. There were, of course, curiosities. In the 1960s, the burgeoning field of radio astronomy began to reveal objects that were inexplicably bright at radio wavelengths. Some of these, like the galaxy Messier 82, seemed disturbed with strange filaments of gas being ejected from its core. Astronomers like Carl Sandage noted its chaotic form and exploding nucleus. It was peculiar and outlier, but its true nature remained a profound puzzle. The available evidence hinted at some kind of unusual energetic process, but the full picture was missing a crucial piece. Theorists speculated about what could power such phenomena. Could it be a supermassive black hole at the galaxy's center, gobbling down matter and spewing out energy? This was a plausible explanation for some active galaxies, the quasars. But for objects like M82, the energy signature didn't quite fit. The light seemed to come from a larger region, not a single point source, and it was shrouded as if happening behind a thick screen. The models were incomplete, hamstrung by a limited view of the cosmic spectrum. We were like observers in a soundproof room watching a symphony orchestra play. We could see the motion, the activity, but we couldn't hear the thunderous music that was actually being produced. The true revolution, the moment the soundproof walls came down, arrived in 1983. NASA, in a joint mission with the UK and the Netherlands, launched the Infrared Astronomical Satellite, or IRAS. Its mission was simple yet audacious: to conduct the first ever all-sky survey in infrared light. For 10 months, IRAS scanned the cosmos shielded from Earth's own heat and sensitive to the thermal glow of objects hidden from optical view. What it found was staggering. It was as if someone had turned on a new set of lights in a dark room, revealing creatures we never knew existed. The sky was littered with brilliant infrared sources. Many were familiar objects like dusty nebulae in our own galaxy, but thousands of them were something else entirely. They were entire galaxies, some of them hundreds of millions of light years away, that were pouring out stupefying amounts of energy as heat. These IRAS galaxies became one of the biggest surprises of modern astronomy. They were dubbed ultra-luminous infrared galaxies, or ULIRGs, for their sheer radiant power. Initially, no one was entirely sure what they were. The data was almost unbelievable. Here were galaxies that were, in terms of total energy output, as luminous as the most brilliant quasars, yet they were almost invisible to optical telescopes. The energy source had to be immense, but it was completely buried in dust. The black hole theory was reconsidered, but for many of these objects the infrared glow was too diffuse. It seemed to emanate from the entire central region of the galaxy, a volume thousands of light years in diameter. Slowly, painstakingly, a new and radical theory began to take shape, connecting the dots between the visual chaos of M82 and the overwhelming infrared glare of the new IRAS galaxies. What if the energy source wasn't a single monster like a black hole, but millions and millions of smaller fires? What if these galaxies were in the throes of a truly biblical episode of star formation? The models began to come together. A massive concentration of gas and dust in a galaxy's core could ignite a firestorm of starbirth. The brilliant, short-lived massive stars would produce the enormous luminosity, and the thick dust would absorb that light and re-radiate it as heat, as infrared light. It fit the observations perfectly. The shrouded appearance, the incredible power, the diffuse nature of the glow, it all pointed to one conclusion. These were not exploding galaxies. They were birthing galaxies on a scale that had never been imagined. The placid, gentle model of star formation, the one we see in our own Milky Way, was suddenly revealed to be just one possibility. It was the default mode, the serene state of being for a mature, stable galaxy. But the universe, it turned out, also had a violent, chaotic, and far more spectacular mode: the starburst. This realization transformed our understanding of galactic evolution. These were not mere curiosities. They were a critical, if fleeting, phase in the life of a galaxy. A phase where a galaxy could produce the bulk of its stellar population in a sudden explosive burst. And with this new understanding came a torrent of new questions. What could possibly trigger such an event? How could a galaxy gather so much fuel into its core to ignite such a firestorm? And what are the consequences of such profligate creation? What happens to a galaxy after it burns through its fuel in a cosmic flash after the fires of the starburst finally die down? The quiet majesty of a spiral arm forming a few stars a year is a process of sustainability. The starburst is the opposite. It is an act of glorious, unsustainable, and ultimately self-destructive creation. To understand its origins, we must look for an equally powerful and disruptive force, something capable of taking the delicate order of a galaxy and shaking it into violent chaos. We must look to the most powerful force of transformation in the cosmos, the collision of entire galaxies. So the question hangs in the cosmic dark, a profound and unsettling mystery. Where does the fuel come from? What force could possibly compress a galaxy's worth of placid quiescent gas and ignite it in a single breathtaking conflagration? The energy required is almost incomprehensible, dwarfing anything our own quiet corner of the universe has ever experienced. To find the answer, we can't look for a simple switch being flipped. We must look for a trigger of unimaginable scale and violence. We must look for the most powerful force in the cosmos, the silent mover of worlds, and the architect of cosmic destiny, gravity. But not the gentle, predictable gravity that holds our Earth in its orbit, or the steady grip that binds the Milky Way into its elegant spiral. We are searching for gravity unleashed. Gravity as a disruptive, chaotic, and creative agent of celestial demolition. The prime suspect in this grand cosmic drama is an event of such staggering proportions that it unfolds not over years or even millennia, but over hundreds of millions of years. A stately, terrifying ballet of gravitational attraction. We're talking about the collision of galaxies. Imagine two immense islands of stars' dust and dark matter, each hundreds of thousands of light years across, drifting through the intergalactic void. For eons they may travel in serene isolation, their internal dynamics governed by a delicate balance. Stars follow their graceful repeating paths. Vast clouds of hydrogen gas, the raw material for future suns, orbit the galactic center in stable, well-behaved disks, too diffuse and too stable to collapse under their own weight. But across the gulf of millions of light-years, they feel a subtle, insistent tug, an invisible tether of gravity reaching out, binding their fates together. Slowly, almost imperceptibly at first, their paths begin to bend. They are now locked in an inescapable gravitational embrace, a slow-motion spiral toward a cataclysmic union. This is not a head-on crash in the way we might imagine. There is too much empty space. The chances of individual stars colliding are infinitesimally small. Instead, this is a battle of gravitational fields, a phantom war waged across vast distances. As the two galaxies draw closer, executing their cosmic waltz, they begin to feel each other's presence in a much more profound way. The force of gravity weakens with distance. This simple fact is the key to everything that follows. The side of a galaxy closer to its approaching partner feels a stronger pull than the side that is farther away. This differential is a stretching force, a cosmic rack. It is the same force that our moon exerts on the Earth, pulling on our oceans to create the tides. But when the objects in question are not a planet and its moon, but two continent-sized collections of 100 billion stars, the effect is magnified to a terrifying and spectacular scale. We call them gravitational tides, and they are the chisels that sculpt the chaos to come. As the galaxies make their first pass brushing past one another in a near miss, these immense tidal forces get to work. They begin to warp the very structure of each galaxy. The elegant flat spiral disks are twisted and distorted like clay being worked on a potter's wheel by an unseen violent hand. Stars and gas clouds are torn from their comfortable circular orbits and flung outwards into the blackness of intergalactic space. From the far sides of each galaxy, vast trailing streams of material are drawn out, creating spectacular luminous arcs that can stretch for hundreds of thousands of light years. These are the great tidal tails, the first visible scars of the encounter. Their ghostly rivers of stars, a testament to the sheer power of the interaction, glowing evidence of a galaxy being literally pulled apart at the seams. Observing these delicate sprawling structures with our telescopes is like arriving at the scene of a cosmic crime and finding the fingerprints of gravity itself imprinted on the fabric of the cosmos. The antennae galaxies, one of the most famous examples of a galactic merger, show us these tales in breathtaking detail. Two magnificent streams of orphaned stars and gas flung into the void, tracing the history of the galaxy's perilous dance. But while these external displays are astonishing, the true engine of the starburst is being primed deep within the galactic cores. The same tidal forces that pull material outwards are also working to push other material inwards. This is the critical step, the mechanism that solves the fuel crisis. Before the merger, the vast reservoirs of molecular gas, the cold, dense clouds needed to form stars, were held in check by their own rotation. Each cloud orbited the galactic center with a specific amount of angular momentum, like a spinning figure skater with their arms outstretched. This momentum created an outward centrifugal force that perfectly balanced the inward pull of gravity, keeping the gas in a stable wide orbit, preventing it from collapsing into the center. The galaxy was a delicately balanced system, slowly sipping its fuel reserve over billions of years. The merger shatters that equilibrium. The gravitational interaction acts like a colossal brake. As the galaxies interpenetrate, their gravitational fields create complex shifting torques, which act on the gas clouds, robbing them of their angular momentum. The spinning skater is suddenly forced to pull their arms in. Their spin accelerates, but their orbit decays. The stable balance is broken. Without the support of orbital momentum, there is only one direction for the gas to go inwards. Across both galaxies, a catastrophic infall begins. Rivers and filaments of cold, dense hydrogen gas, once spread thinly across tens of thousands of light years, are now funneled down into the gravitational heart of the merging system. What was once a placid reservoir becomes a raging, turbulent cascade. Imagine a dam bursting with the full weight of the water behind it, now channeled into a narrow, violent canyon. This is what happens to the interstellar medium. Vast quantities of gas, equivalent to billions of times the mass of our Sun, are dumped into a tiny region just a few thousand light-years across. The concentration of raw star-forming fuel becomes almost unimaginably dense. It is a cosmic pressure cooker, and the temperature and pressure are rising exponentially. This isn't theoretical guesswork or a computer simulation run in a lab. We have seen this process happening captured in astonishing detail by our most advanced observatories. When we point the Hubble Space Telescope at a system like the Mice galaxies, we see the tidal tails, the distorted disks, the telltale signs of a gravitational brawl. But Hubble sees primarily invisible light, the light of stars. The real action, the movement of the cold gas that fuels the starburst, is hidden. It is shrouded in colossal cocoons of dust, opaque to optical telescopes. To peer into this maelstrom, we need different eyes. We need to see the universe in infrared and radio wavelengths. This is the realm of the James Webb Space Telescope and the Atacama Large Millimeter Submillimeter Array, or ALMA. When JWST gazes upon a merging system like Stephan's quintet, its powerful infrared vision pierces through the obscuring dust veils. It reveals the furious shockwaves propagating through the gas as one of the galaxies plows through the others at over 2 million miles per hour. We see the gas being compressed and heated, glowing with the fury of the collision. We are witnessing in real time the feeding of the monster. ALMA, a vast array of radio dishes in the high deserts of Chile, gives us an even more fundamental view. It is tuned to detect the faint cold glow of the molecular gas clouds themselves. With ALMA we can map the flow. We can trace the great streams of gas as they are stripped from the galactic disks and channeled down these gravitational funnels. In images of ARP 220, an advanced merger and one of the most luminous starbursts known, ALMA reveals two distinct counter-rotating disks of gas in the core, each containing more gas than the entire Milky Way galaxy, crammed into a space just a few hundred light-years across. They are the remnants of the two original galactic cores now swirling around each other in a final deadly embrace. Here, the evidence is undeniable. We are watching the fuel for a starburst of apocalyptic proportions being delivered directly to the ignition point. It is the ultimate cosmic pile-up, a concentration of matter so extreme that the outcome is as violent as it is inevitable. Once this colossal reservoir of gas has been assembled in the galactic centre, the final stage is set. The sheer density is staggering. Clouds that were once light-years apart are now crushing into one another. The pressure skyrockets to levels unseen in a normal galaxy. Everywhere within this compact turbulent core, the conditions for star formation are met simultaneously. A critical threshold is crossed. The gas clouds can no longer support their own weight. Under the relentless squeeze of gravity, they begin to collapse. But this isn't the gentle, isolated collapse that forms one or two stars in our stellar neighbourhood. This is a synchronized, cascading failure of an entire galactic core's worth of gas. A chain reaction is triggered. The collapse of one massive cloud sends shockwaves into its neighbours, triggering their collapse, which in turn triggers others. Suddenly, across a region spanning thousands of light-years, the entire reservoir of gas ignites in a furious, synchronized burst of creation. This is the starburst. For a brief glorious period lasting perhaps only a few tens of millions of years, a blink of an eye in cosmic time, the core of the merging galaxy becomes the most violent and prolific star factory in the universe. Hundreds, sometimes thousands of new suns are born every single year. Among them are the true monsters of the cosmos, massive blue-white stars, dozens of times more massive and millions of times brighter than our own sun. These celestial blowtorches burn through their fuel with ferocious intensity, bathing the dense, dusty core in brilliant, searing radiation. The galaxy, once a quiet spiral, is transformed into a seething cauldron of stellar birth. Its luminosity skyrockets, outshining its former self by a factor of 100 or even 1,000, becoming one of the brightest objects in the cosmos. The mystery of the engine is solved. It is the raw, untamed power of gravity, using the collision of entire galaxies as the mechanism to gather and compress fuel on an industrial scale. The starburst is the spectacular, inevitable firestorm that erupts from the wreckage of this cosmic train wreck. The process is beautiful in its terrifying efficiency. The long, slow dance of the merger, the elegant creation of tidal tails, the brutal and chaotic funneling of gas, and the final explosive ignition. It is one of the most extreme transformative processes the universe has to offer, turning two ordinary galaxies into a single luminous beacon. This violent pathway to creation seems to be a fundamental chapter in the life of many galaxies, a necessary trauma that forges a new future from the crucible of the old. But looking at these incredible cataclysmic events, a new set of questions begins to emerge. This process is so extreme, so all-consuming. Is this truly the only way must a galaxy endure such a trial by fire to experience this level of creation? Or are there other more subtle mechanisms at play, hidden within the intricate structures of galaxies that have never suffered such a violent fate? The search for the trigger has led us to the grand drama of galactic collisions, but the story of starbursts we are beginning to find may be even more complex than we ever imagined. And so this crucible of creation burns with an impossible transient glory. A light so fierce it eclipses 1,000 ordinary galaxies, a beacon blazing across billions of light-years of cold, empty space. But this celestial fire, you must understand, comes at a terrible price. For every single one of those brilliant blue, massive stars we see as living on borrowed time, burning through its nuclear fuel with a recklessness that seals its own violent fate. Inside their cores, a frantic race is underway against the crushing force of gravity, a race they are all destined to lose. What we are witnessing is not just a birthing suite, but a death row, a cosmic engine that manufactures its own agents of destruction. These stellar titans, some weighing more than 100 times our own sun, live for only a few million years, a mere blink of an eye in cosmic terms. They are the rock stars of the universe, they live fast and they die young. While a star like our sun will gently simmer for 10 billion years, these behemoths are a continuous raging explosion, fusing hydrogen into helium, then helium into carbon, and onwards up the periodic table in a desperate layered frenzy. Carbon becomes neon, neon becomes oxygen, oxygen becomes silicon. Each stage burns hotter, faster, more violently than the last, a frantic sequence of escalating desperation at the heart of the star. The star swells its outer layers, churning its core temperature, soaring into the billions of degrees, a point of unimaginable intensity. Then finally the process reaches iron, and at iron the frantic alchemy of fusion stops dead. Fusing iron consumes energy. It does not release it. The fire at the heart of the star, the furnace that held gravity at bay for eons, is extinguished in less than a second. Catastrophe is no longer a possibility. It is an inevitability. The star's own colossal mass becomes its executioner. In an instant, the immense outer layers, billions upon billions of tons of matter, begin to fall inward, collapsing under their own weight. They accelerate to nearly a quarter of the speed of light, crashing down onto the now inert iron core. What happens next is not merely an explosion. It is the universe tearing itself apart to announce the death of a king. The core, compressed beyond all known limits of physics, rebounds with a titanic shockwave of pure, unrestrained power. This shockwave, a wave of raw energy, screams back out through the infalling layers, reversing the collapse in the most violent event the cosmos can produce: a single supernova. For a few brilliant weeks, it will outshine the entire galaxy that birthed it, unleashing more energy than our sun will in its entire lifetime. It is a final defiant roar of atomic fire, a funeral pyre visible across the universe. Now imagine this event not as a singular, isolated spectacle. Imagine it happening again and again and again in a relentless percussive rhythm. In a starburst galaxy, you don't have one supernova every century like in our Milky Way. You have dozens, hundreds, even thousands exploding every single year. One star detonates here, its shockwave slamming into a neighbouring gas cloud. Another erupts over there, its flash of gamma rays sterilizing everything for light years. It's a cascade, a chain reaction of stellar death on a galactic scale. The heart of the starburst becomes a minefield, a perpetual cosmic blitz. The shockwaves from these countless detonations don't just dissipate, they collide, they merge, they amplify each other. Individual ripples of destruction coalesce into a tidal wave of unimaginable force. A single unified bubble of superheated gas and radiation, expanding outwards from the galactic core like a thunderclap in slow motion. This is the birth of something new, a phenomenon born from synchronized death. This is a galactic wind. It is not a gentle breeze, it is a hurricane of plasma heated to millions of degrees and moving at thousands of kilometers per second. A ghost of the stars that created it, carrying their fury outwards. This wind is the galaxy's great feedback mechanism, its method of self-regulation. It is the violent consequence of its own unchecked fertility. As this super wind tears through the galaxy's spiral arms, it acts like a cosmic sandblaster, a celestial leaf blower of epic proportions. It slams into the dense cold clouds of molecular gas, the very reservoirs that were queued up to form the next generation of stars. Instead of being allowed to collapse under their own gravity, these nurseries are flash-heated, shredded, and violently pushed aside. Star formation in the path of the wind is instantly halted. The factory is being dismantled by its own products. The wind carves out vast empty cavities within the galactic disk, some stretching for thousands of light years like immense bubbles blown in the cosmic soap film of the galaxy. From a distance, these galaxies can appear hollowed out as if some great beast has taken a bite from their very soul. But the wind's influence extends far beyond simply rearranging the local furniture. Its power is so immense, its velocity so extreme, that it can overcome the galaxy's own gravitational grip. It doesn't just push gas around inside the galaxy, it blasts it clean out of the system forever. This is a galactic exodus, a mass expulsion of the very substance of life. Trillions of tons of hydrogen and helium, the raw fuel for future suns, are launched into the desolate empty void between the galaxies, and riding this incredible outflow like ashes from a great fire are the precious newly forged heavy elements. The carbon, the oxygen, the silicon, the iron, all the materials synthesized in the hearts of those dead stars and blasted into space by their supernova. Death throes are now caught in this galactic hurricane. These elements, the building blocks for planets, for asteroids, for life itself, are not being kept to enrich their home galaxy. They are being exiled. The starburst in its fury is seeding the universe. It is polluting the pristine empty darkness of the intergalactic medium, enriching that void with the potential for future distant creation. It is an act of simultaneous destruction and profound cosmic generosity. The galaxy is immolating itself to fertilize the cosmos. It is a process so violent, so seemingly chaotic, that for decades we believed it was the only major force at play, the sole governor of a starburst's fate. We were wrong. Because deep within that chaotic, supernova-driven maelstrom lurking in the gravitational heart of the galaxy, another even more powerful monster is stirring. Every major galaxy we now know has a secret, a dark heart. At its precise gravitational center lies a supermassive black hole. Not the stellar mass kind left behind by a single dead star, but a true leviathan, a singularity weighing millions or even billions of times the mass of our Sun. In a quiet galaxy like our own, this central engine is mostly dormant, a sleeping giant occasionally snacking on a stray star or gas cloud. Its influence is subtle, a quiet gravitational anchor for the stars orbiting around it. But in a starburst galaxy there is nothing subtle. The same violent gravitational dynamics that triggered the starburst, the galaxy mergers, the colliding gas clouds, do not just feed the star factories in the disk. They create a torrent of matter flowing towards the galactic center, a river of gas and shredded stars spiraling down into the maw of the beast, and a sleeping giant, when fed, awakens. And it awakens with a fury that can dwarf even the light of 1 billion stars. As this material cascades towards the event horizon, it doesn't fall straight in. It is whipped into a frenzy, forming a flattened spinning vortex of matter, known as an accretion disk. Here, friction magnetic fields and sheer gravitational shear heat the gas to temperatures of millions of degrees hotter than the core of any star. The disk begins to glow with an incandescent, mind-boggling intensity, shining in high-energy X-rays and ultraviolet light. The placid galactic center ignites, transforming into an active galactic nucleus, or AGN. If it becomes powerful enough, we call it a quasar, the most luminous single object in the entire universe. This is the second form of feedback, a force originating not from millions of stars but from a single gravitationally dominant point, and its relationship with the starburst surrounding it is one of the most complex and fascinating dances in all of cosmology. At first, this newly awakened monster can seem like an accomplice. The intense radiation blasting from the accretion disk can push on nearby clouds, compressing them and potentially triggering localized bursts of new star formation right in the galactic core, a phenomenon we call positive feedback. Furthermore, as the black hole spins, it twists the magnetic fields in the disk into colossal focused funnels above and below it. Through these funnels, it can launch twin jets of energized particles at nearly the speed of light. These relativistic jets can slam into the dense gas of the galactic disk, creating powerful shock waves that, like their supernova counterparts, can compress gas and initiate the birth of yet more stars. The black hole appears to be fanning the flames, adding its own unique brand of creative violence to the starburst already in progress. It is a terrifying but seemingly productive partnership. But this alliance between the black hole and the star-forming frenzy is a fragile one, a devil's bargain destined to sour. As the inflow of gas continues, the accretion disk around the black hole grows hotter, brighter, and more powerful. The energy it radiates outwards begins to build into an unstoppable force, a relentless pressure of pure light. The jets it launches become more stable, more energetic, drilling out of the galactic core like cosmic blowtorches. A tipping point is reached. The central engine's power output becomes so overwhelming, so utterly dominant that its role flips from creator to destroyer. This is negative feedback, and it is the ultimate kill switch. The flood of X-rays and ultraviolet radiation from the quasar is no longer a gentle nudge to nearby gas clouds. It becomes a sterilizing blast, superheating the gas across the entire galaxy. Cold, dense molecular gas, the delicate fuel for starbirth, is energized, puffed up and evaporated by this onslaught. It becomes too hot and too diffuse to ever collapse and form stars again. The galactic nurseries are not just pushed aside as with the supernova winds, they are vaporized in place. At the same time, the black hole's powerful jets, now extending for tens of thousands of light years above and below the galactic plane, act as conduits, helping to channel the hot gas and supernova debris out of the galaxy even more efficiently. The two feedback mechanisms, one from the stars, one from the black hole, begin to work in devastating concert. The supernova winds blow from the inside out. The quasar radiation bakes from the center outwards. The jets provide a convenient exhaust chute. Together they form an inescapable trap of destructive energy. The starburst is choked, starved, and ultimately extinguished. The galaxy is quenched. The very process that ignited the starburst, the massive inflow of gas, also awakened the agent of its own demise. It is the ultimate cosmic paradox, a perfect self-regulating loop of creation and annihilation. The galaxy, in its moment of supreme brilliance, effectively commits suicide. What we are witnessing is a battle for the soul of a galaxy played out between two of the most powerful forces in the universe. On one side, the collective power of millions of short-lived massive stars driving a hurricane of matter outwards. On the other, the singular focused might of a central supermassive black hole, unleashing torrents of radiation and relativistic plasma. Sometimes these forces seem to oppose one another, a chaotic push and pull. At other times, they synchronize, working together to purge the galaxy of its fuel. Which force dominates and when likely depends on the specific galaxy, its mass, the nature of its merger, the size of its black hole. It is a complex, messy, and profoundly beautiful interplay of physics on a scale that almost defies human comprehension. The end result, however, is often the same. The starburst frenzy cannot last. It burns too brightly. Whether it is the supernovae that blow it out or the central quasar that snuffs it out, or most likely a conspiracy between the two, its fate is sealed. The brilliant blue light of young, massive stars begins to fade, unreplaced by a new generation. The galactic winds slow as the supernova rate plummets. The central quasar dims as its fuel supply is finally cut off. An eerie silence begins to fall over the once chaotic galactic core. The cosmic factory has shut down. The fire is out. The galaxy is left exhausted, hollowed out, and profoundly changed. It is now a shadow of its former brilliant self, littered with the corpses of dead stars, neutron stars, and stellar black holes, and populated only by older, cooler, redder suns. It has aged 1 billion years in the span of a few million. So what happens now? What becomes of this ghost of a galaxy, its creative potential spent? And more mysteriously, what of the vast enriched cloud of its own making? Now drifting silently in the intergalactic dark, a ghostly testament to the fire from which it was thrown. And so after a fury that has raged for 100 million years, a change begins. The crescendo of creation, the blinding light of 1 million stellar births igniting in unison, cannot sustain itself. An entire galaxy running a cosmic fever has burned through its inheritance with a profligate, impossible speed. The celestial engine that screamed with power now begins to sputter. What follows the firestorm is not peace, but an exhaustion so complete, so profound, that it will redefine the very soul of the galaxy for all of time. We are now entering the long twilight of the starburst, the beginning of a great and terrible silence. You're witnessing the inevitable consequence of living too fast. Think of the galaxy's reservoir of cold molecular gas not as an infinite ocean, but as a finite tank of fuel. A normal spiral galaxy, like our own Milky Way, is a model of efficiency. It sips its fuel, carefully rationing it over billions upon billions of years, creating a steady, gentle stream of new stars. It is a marathon runner pacing itself for an unimaginably long journey. The starburst galaxy, by contrast, is a sprinter that has run the entire race in the first 100 meters. It has ripped open the fuel tank and thrown a match. In the chaotic heart of the merger that sparked this event, vast clouds of hydrogen, once scattered peacefully across tens of thousands of light years, were violently compressed. They were funneled into a compact turbulent core, a pressure cooker of cosmic proportions. This concentration of resources is what made the inferno possible, but it also sealed the galaxy's fate. The star formation rate, 1,000 times that of a quiet galaxy, became a ravenous hunger. Every million years, a quantity of gas equivalent to hundreds of suns was crushed into new stars. There was no time for replenishment. No slow, graceful infall of pristine gas from the intergalactic medium could possibly keep pace with such a voracious appetite. The galaxy was in a very real sense eating itself alive. We can see this cosmic famine beginning in the spectral signatures of these dying giants. The telltale glow of ionized hydrogen, the vibrant pinks and reds that are the signposts of stellar nurseries, begins to dim. The cosmic cold, once the cradle of life, now becomes a tomb. The molecular clouds, once dense and fertile, are now shredded and depleted, their substance transmuted into the burning hearts of infant stars. This process of depletion is an inexorable countdown. Like a fire starved of oxygen, the star formation must slow down. But what we observe is something far more dramatic, far more sudden than a gentle fading away. It is not a slow decline into old age. It is a sudden, violent cessation, a switch being thrown. Astronomers call this event quenching, a term that feels almost too gentle for the cataclysm it describes. This is not the gentle quenching of a thirst, but the violent plunging of white-hot steel into cold water. It is the universe actively shutting down the factory of creation. For decades, we believed this was a simple story of resource management. The galaxy runs out of gas, so it stops making stars. The truth as we've come to understand it is far more complex and far more violent. The galaxy doesn't just run out of fuel, it actively ejects what little it has left. It sterilizes itself. The culprits behind this galactic shutdown are the very children of the starburst itself, its most massive stars, and the supermassive black hole now raging at its core. The superwinds we witnessed earlier, those magnificent outflows of gas driven by thousands of supernovae, were merely the opening salvo. As the most massive of the new stars, behemoths 100 times the mass of our Sun, reach the end of their brief spectacular lives, they detonate. They explode with a fury that can temporarily outshine the entire galaxy. For millions of years, these explosions have been a constant drumbeat, a rhythm of destruction, accompanying the symphony of creation. Now, as the last generation of these giants dies out, their combined energy creates a final devastating pulse. A shockwave of unimaginable power, a supernova feedback that acts like a colossal broom sweeping through the galactic disk. It scours the remaining pockets of cold gas, heating them to millions of degrees. Gas that is superheated cannot collapse to form stars. It becomes a thin, useless plasma, too energetic and diffuse to ever feel the gentle pull of its own gravity again. This isn't just using up the fuel, this is poisoning the well for any future generations. But even this cosmic bombardment pales in comparison to the final act of quenching delivered from the very heart of the galaxy. Deep within the core, the supermassive black hole, which has been gorging itself on the infall of gas, awakens with a terrible power. The accretion disk swirling around its event horizon becomes the most luminous object in the universe, a quasar. It is a celestial blowtorch unleashing jets of high-energy particles and radiation that rip through the galaxy at nearly the speed of light. This is active galactic nucleus, or AGN feedback. It is the ultimate regulatory mechanism. The black hole, the nexus of gravity, becomes the agent of expulsion. These jets, focused and relentless, drill their way out of the galactic core. They slam into the remaining gas clouds with a force that defies imagination, driving them out of the galaxy's gravitational grasp entirely. This is a cosmic eviction on the grandest of scales. The galaxy's last hope for a future of starbirth is hurled into the desolate emptiness of intergalactic space, a final ghostly plume marking the death of an era. The factory is not just closed, it has been dismantled and its parts scattered to the cosmic winds. The silence that descends is now permanent. The galaxy is quenched. It has become a relic, a ghost town of stars with no hope of renewal. And with the cessation of violence, a new slower but equally profound transformation begins. The galaxy's very structure, its identity, has been irrevocably broken. Before the starburst, it was likely a majestic spiral, a pinwheel of delicate arms and ordered celestial beauty. Its stars moved in elegant near-circular orbits within a flattened disk, a gravitational gyroscope spinning in the darkness. The merger and the subsequent starburst shattered that order. Imagine two spinning disks of glass colliding. The result is not a larger, more perfect disk, but a chaotic spray of shards. So it is with the stars. Their once orderly orbits were thrown into disarray. The gravitational potential of the galaxy was violently and rapidly rewritten. Millions of new massive stars were not born into the calm plane of the old disk, but in a turbulent three-dimensional firestorm at the centre. This new mass distribution acts like a powerful gravitational churn. The old stellar populations, the quiet, long-lived stars from before the merger, are pulled from their circular paths. Their orbits are twisted, torqued and randomized. They are flung high above and below the old galactic plane, their momentum scattered in all directions. This process, known as violent relaxation, is the galaxy attempting to find a new equilibrium after a traumatic shock. It is the gravitational memory of the system being erased and rewritten. It is a slow cosmic settling. Over hundreds of millions of years, the delicate spiral arms, which were nothing more than density waves of gas and young stars, simply dissolve. There is no new gas to replenish them, and the gravity of the chaotic new stellar distribution pulls them apart. The thin, elegant disk bloats, thickening into a vast, featureless spheroid. What we are watching is a metamorphosis. The graceful butterfly of a spiral galaxy is being pressure-cooked back into a simple, robust cocoon. The final shape is dictated by chaos, not order. The stars no longer orbit a common centre in a unified dance. Instead, their paths are like a swarm of bees in a box, random, eccentric, and buzzing in 3 dimensions. The resulting structure is a colossal, shimmering ball of stars, an elliptical galaxy. This is one of the most profound revelations in modern astrophysics, that the universe's most violent and creative events, starbursts, are the primary mechanism for forging its most serene and ancient-looking galaxies. The fiery blue, chaotic youth of a starburst galaxy gives way to a calm, red, and ordered old age as an elliptical. It is a life cycle written in violence and ending in a quiet, majestic stillness. The starburst was the chaotic crucible that forged this new stable state. But the transformation is not merely structural, it is also alchemical. The very chemistry of the galaxy has been permanently altered. Those massive blue stars that powered the starburst were not just sources of light, they were nuclear forges. In their cores, they fused hydrogen and helium into heavier elements, carbon, oxygen, silicon, iron, all the elements necessary for rocky planets for life for us. In their explosive deaths, they seeded the galaxy with this precious material. The superwinds that scoured the galaxy were not just winds of hydrogen. They were enriched with the ashes of 1,000 suns. A post-starburst galaxy is fundamentally richer in these metals, the astronomical term for any element heavier than helium, than it was before. This chemical enrichment is the starburst's most enduring legacy. Even the gas that was violently expelled into the intergalactic medium carries these seeds. This enriched material can then rain down on other smaller galaxies, or eventually cool and collapse to form new generations of stars and planets in entirely different systems billions of years in the future. The starburst in its death has enriched the universe around it. It has paid a cosmic price, sacrificing its own future to fertilize the cosmos. Inside the newly formed elliptical galaxy, this chemical legacy is locked away. The stars that remain are a mixture of the old metal-poor populations from the progenitor spirals and the new metal-rich generations born in the fire. But with star formation now permanently halted, this chemical signature is frozen in time. The galaxy becomes a celestial fossil, preserving the chemical memory of its violent past for eternity. Studying the elemental abundances in these red and dead galaxies allows us to perform a kind of cosmic archaeology, piecing together the story of the cataclysm that created them. As the last blue giants flicker and die, a profound colour shift sweeps across the galaxy. The brilliant searing blues and whites of young hot stars are replaced by the gentle golden glow of older cooler stars like our own Sun. As these stars too age over billions of years, they will swell into red giants. The galaxy's overall colour will shift inexorably towards red. It becomes a vast crimson sphere, a city of 1 trillion ancient suns. This is the final state, a red and dead elliptical galaxy. It is a place of profound tranquility, a place where the storms have passed and the dust has settled quite literally. There are no glowing nebulae, no stellar nurseries, no hint of renewal. There is only the steady collected light of ancient stars on their long, slow journey towards oblivion. It is a beautiful but desolate fate. This galactic giant, once the most dynamic and productive object in its cosmic neighbourhood, is now quiescent. It has settled into a quiet retirement, its creative life over. It will drift through the cosmos for eons, a monument to the ephemeral fury of its past. Its primary role in the universe has shifted. It is no longer a creator, but a gravitational anchor. Its immense mass, now centrally concentrated, warps the fabric of space-time, shepherding smaller satellite galaxies and holding together the vast architecture of its local galaxy cluster. It has exchanged the vibrant chaos of youth for the stable gravitational authority of old age. But is the silence ever truly absolute? Is the quenching truly forever? The galaxy is a ghost of its former self, yet it is saturated with the chemical potential for new life. It holds within its ancient stars the very elements required to build worlds like ours. The fuel is gone, but the blueprints remain. It exists now on a precipice between memory and future, a testament to the idea that in the universe, the most transformative events are often the most fleeting. The starburst phase, that brilliant defining moment of madness, was but a flash in the pan of cosmic time. Yet that single flash has determined the fate of 1 trillion suns, and perhaps the fate of an entire cosmic neighbourhood. We are left with a spectre, a beautiful, haunting relic whose story is now complete. Or is it? For even in this silent stellar graveyard, the universe may yet have a final, surprising chapter to write. We have journeyed deep into the heart of the furnace, witnessing the relentless, explosive cycle of creation and destruction that defines a starburst. We've seen the incandescent nurseries where stars are born by the million, and we have felt the reverberations of their violent supernova deaths. But to leave our understanding there confined within the boundaries of a single galaxy would be to miss the point entirely. The true significance of these cosmic crucibles isn't merely what they are, but what they have done for the universe itself. Their story is not an isolated chapter of violent astrophysics. It is the foundational text from which the entire grand narrative of cosmic evolution was written. To grasp their importance, we must pull our perspective back away from the glittering core of M82 or the antennae and travel much further. We must go back to a time before galaxies as we know them even existed, to an epoch of profound and overwhelming darkness. Imagine the universe in its infancy a few 100 million years after the Big Bang. The primordial fireball is cooled, its light stretched and faded into the microwave background. Stars have not yet truly ignited on a grand scale. The cosmos is filled with a vast, featureless and chillingly neutral fog of hydrogen gas. This was the cosmic dark age. It was a universe without light, without structure, a silent, waiting expanse of potential. For millions of years, gravity was the only active force patiently pulling the first clumps of matter together, but the universe remained transparent to nothing, a spectral prison from which light could not escape. Any fledgling star that did ignite found its ultraviolet rays immediately absorbed by the surrounding hydrogen. its energy trapped like a shout in a soundproof room. For life for planets, for us to even exist, something had to happen. Something had to burn away the fog. This monumental transformation, the most significant event since the Big Bang itself, is known as the Epoch of Reionization. It was the moment the universe took its first breath of light, the moment the Dark Ages ended, and the cosmos we recognize today began to emerge. For decades, astronomers searched for the source of this universe-altering event. The prime suspects were the quasars, the hyperluminous cores of galaxies powered by supermassive black holes. Their light is ferociously powerful, capable of punching holes through the cosmic fog for immense distances. Yet as our surveys of the early universe became more comprehensive, a problem emerged. There simply weren't enough of them. Quasars were too rare in that primordial epoch, too scattered to have collectively accomplished a task of such staggering scale. They were cosmic lighthouses, brilliant but isolated, incapable of illuminating the entire ocean. The answer we now realize was not a few colossal beacons, but an uncountable swarm of celestial blowtorches. The culprits were the universe's very first starburst galaxies. They were smaller, messier, more chaotic than their modern descendants, but what they lacked in size they made up for in sheer, unadulterated ferocity and number. Billions of them igniting across the cosmos, each one a compact engine of stellar genesis. The immense torrent of ultraviolet radiation pouring from their legions of young, massive blue stars was the key. But even this presented a puzzle. How did that sterilizing, fog-clearing light escape its own cradle? As we've seen, a starburst galaxy is choked with the very same gas and dust from which its stars are born. The light should have been trapped, absorbed locally before it could ever reach the intergalactic medium. The solution lies in the very violence we have witnessed. The synchronized detonations of thousands of supernovae within these compact galaxies did more than just trigger more star formation. They acted as a cosmic sandblaster. The superwinds they generated, those galactic-scale hurricanes of hot gas and radiation, tore open channels and chimneys through the dense interstellar medium. They ripped holes in the very fabric of their host galaxies, creating escape routes for the trapped ultraviolet photons. It was a self-perpetuating process of liberation. The more stars that formed, the more supernovae exploded. The more supernovae that exploded, the more powerful the wind became, clearing wider and wider escape paths for the light of the next generation of stars. Each tiny starburst galaxy became a leaky sieve, pouring its ionizing radiation out into the dark, empty spaces between galaxies. Individually, the contribution of each was small, a pinprick of light in an endless dark. But there were billions of them, and over hundreds of millions of years their collective effort achieved the impossible. Their overlapping spheres of influence grew merged and finally consumed the last vestiges of the neutral hydrogen fog. The universe-spanning prison of gas was dismantled atom by atom. The cosmos became transparent, allowing light to travel across billions of light-years, revealing the intricate tapestry of the cosmic web for the first time. This was not just a sunrise, it was the installation of the firmament, and we are only now, with our most powerful new eyes, beginning to witness this ancient genesis directly. Peering back across more than 13 billion years of cosmic history, the James Webb Space Telescope is capturing the faint red-shifted light of these primordial liberators. We expected to see the first grand majestic galaxies. Instead, Webb is revealing something far more profound. It sees a cosmos teeming with small, intensely blue and furiously active galaxies. These are the starbursts that ended the Dark Ages. They are not the neat spirals or stately ellipticals of our local universe. They're irregular, clumpy and ablaze with the fires of their first and most violent period of creation. We are seeing for the first time the architects of the illuminated cosmos caught in the very act of burning away the primordial gloom. Every distant galaxy Webb reveals is not just a scientific curiosity, it is a testament to the power of the starburst phenomenon. Each one is a piece of the puzzle, a single candle in the legion that collectively set the universe alight. It is a staggering realization to finally see the engines that fashioned the transparent, star-filled reality we inhabit. But clearing the cosmic fog was only their first act of cosmic engineering. Illuminating the universe was a monumental achievement, but creating the substance of the universe was arguably an even greater one. The Big Bang left behind an extraordinarily simple cosmos, composed almost exclusively of the two lightest elements, hydrogen and helium. It was a universe of gas with no solids, no complexity, no potential for the rich chemistry that life demands. Every other element on the periodic table, the carbon in your DNA, the oxygen you breathe, the silicon in the rocks beneath your feet, the iron in your blood had to be forged. It had to be created one atomic nucleus at a time inside the hearts of stars, and once created, it had to be distributed. Forging these precious heavy elements is one thing. Delivering them across the cosmos to seed future generations of stars and planets is another challenge entirely. Massive stars, the kind that dominate a starburst, are the primary furnaces for this cosmic alchemy. In their cores, under unimaginable pressures and temperatures, they fuse hydrogen and helium into carbon, nitrogen, oxygen, and all the elements up to iron. When these stars die in the colossal supernova explosions that punctuate the life of a starburst galaxy, they perform one final magnificent act of creation. The shockwave of the explosion itself is so energetic that it forges the elements even heavier than iron, gold, platinum, uranium, and then blasts this entire inventory of freshly minted material out into the interstellar medium. A normal galaxy like our own Milky Way does this slowly, gracefully over billions of years. Stars are born, they live their lives, they die, and their elemental ashes are gently mixed back into the galactic gas, enriching it over cosmic timescales. It is a slow, almost stately process of gradual enrichment. A starburst galaxy, however, operates on an entirely different principle. It is not a gentle cycle, it is an industrial-scale element factory, and a continental-scale distribution system rolled into one. The sheer concentration of massive stars means that heavy elements are not produced in a trickle but in a deluge, and the mechanism for their distribution is not gentle mixing but violent expulsion. Those same galactic superwinds that carved escape routes for ultraviolet light perform a second vital function. They are the universe's great elemental dispersal system. When the wind erupts from the galaxy's core, it doesn't just carry hot gas. It carries the entire payload of heavy elements forged by its millions of dying stars. It is a tsunami of carbon, a hurricane of oxygen, a blizzard of silicon and iron ejected from its galactic birthplace with ferocious velocity. This material is blasted clear out of the galaxy's gravitational grasp and propelled deep into the voids of intergalactic space. These elemental seeds travel for millions of light years across the cosmic web, contaminating the pristine hydrogen and helium clouds that would otherwise have formed only first-generation metal-poor stars. Thanks to the starbursts, the next generation of galaxies and stars could form from gas already seasoned with the building blocks of complexity. It is because of these ancient violent outflows that a star like our Sun could form with enough heavy elements to create a rocky planet like Earth. The starbursts didn't just build their own stellar populations, they seeded the entire universe with the potential for planets for geology, for chemistry, and ultimately for biology. They are the ancestors of all complexity. This is not speculation. With instruments like the Atacama Large Millimeter, Submillimeter Array or ALMA, we can now directly observe these processes unfolding across cosmic time. ALMA is uniquely sensitive to the cold gas and dust that make up the raw material of galaxies. When it turns its 66 coordinated eyes towards a distant starburst, it doesn't just see the light of the stars. It can trace the immense outflowing plumes of element-rich gas mapping the galactic superwinds in exquisite detail. We can see the material leaving the galaxy. We can measure its speed, its temperature, and even its chemical composition. We can see carbon monoxide and ionized nitrogen being hurled into the intergalactic medium at millions of miles per hour. We are watching in real time the enrichment of the universe. We see these galaxies actively polluting their cosmic neighborhoods with the very elements necessary for life. Combining the vision of Webb and ALMA gives us a breathtakingly complete picture. Webb shows us the brilliant compact light of the stars themselves, the engine of the process revealing the moment of reionization. ALMA shows us the consequence, the cold, dark element, rich exhaust pouring out into the cosmos the raw material for future worlds. Together they provide incontrovertible evidence that these hyperactive galaxies are the master architects of the modern universe. They are not merely an interesting or extreme subclass of galaxy. They are a fundamental and indispensable stage in the evolution of the cosmos. Without their combined fury, the universe might have remained dark, shrouded in its primordial fog. Without their violent creative exhalations, the cosmos would have remained a simple sterile place, a sea of hydrogen and helium incapable of producing a single grain of sand, let alone a conscious being to marvel at its existence. So when you look at an image of a starburst, you are not just seeing a distant violent spectacle. You are looking at a machine that fundamentally reshaped reality on the largest possible scale. You are seeing the process that first lit up the dark. You are seeing the forges that created the atoms in your body, and you are seeing the distribution network that delivered those atoms across billions of light years of space and billions of years of time to a quiet spiral arm of the Milky Way, where they could eventually coalesce into our solar system, our planet and us. These galaxies are more than just celestial objects. They are our most distant and powerful ancestors. Their story is our story, their violence, our genesis, their legacy, written in the very substance of our world and our bodies. The light from these ancient factories is a message from our own deep past, telling us how the stage was set, how the darkness was banished, and how the universe was seeded with the promise of life. And so the fever breaks. The violent, desperate pulse of star formation, which once burned with the fury of a billion suns, begins to slow. The colossal blue giants, those ephemeral titans that lived fast and died young, have almost all exploded, their final incandescent death cries echoing through the thinning interstellar clouds. What remains is a galaxy transformed, scarred and sanctified by its ordeal. We have journeyed through the heart of this cosmic furnace, witnessing a spectacle of creation and destruction on a scale that defies terrestrial imagination. We have seen clouds of pristine hydrogen hundreds of thousands of light years across, compressed by the inexorable crush of gravity, collapsing into dense knots of protostellar fire. From within these dusty cocoons, we watched as stellar embryos ignited their nascent light, tearing through the obscuring veil in a breathtaking display of cosmic birth. We saw these newborn stars coalesce into magnificent superclusters, glittering swarms of light so dense they warped the very fabric of their surroundings. These were not the gentle, sparsely populated stellar nurseries of our own Milky Way, but brutal, crowded celestial cities where gravitational encounters were common and stellar lifespans were tragically short. The most massive of these stars, burning through their nuclear fuel, with reckless abandon, blazed with a light millions of times brighter than our own sun. They were the celestial blowtorches that ionized the surrounding gas, carving vast empty bubbles into the galactic interior and painting the cosmos with ethereal glowing nebulae. Their existence was a frantic, beautiful sprint, a momentary triumph of fusion over gravity. And we followed them to their cataclysmic end. Their deaths in the form of supernova explosions were even more spectacular than their lives. In these final titanic blasts, we saw the universe's grand alchemy at work. The simple elements forged in the Big Bang, hydrogen and helium, were transmuted in these stellar cores into the heavier elements that make existence as we know it possible. The carbon in your DNA, the oxygen you breathe, the calcium in your bones and the iron in your blood. We witnessed their genesis in the heart of a dying star. These explosions in turn sent shockwaves propagating through the galaxy, compressing yet more gas and triggering a new ferocious wave of star formation in a relentless self-perpetuating cycle of death and rebirth. It is a process of cosmic recycling on the grandest scale imaginable, where the ashes of one generation of stars become the building blocks of the next. This duality, this inseparable dance of creation and destruction, lies at the very heart of the starburst phenomenon. To forge a new star, you must first destroy a tranquil gas cloud. To forge the elements of life, you must first destroy a star. The starburst galaxy, in its glorious chaotic brilliance, is the ultimate expression of this fundamental cosmic truth. It is both a cradle and a tomb, a factory that consumes its own raw materials with an insatiable hunger, burning through in a few million years what normal galaxy might leisurely use over billions. It is a galaxy living on borrowed time, spending its entire inheritance in a single, magnificent and ultimately unsustainable burst of creative energy. The galactic winds we traced, those ghostly outflows of superheated gas and heavy elements, are the exhausted breath of this dying fever. They are the evidence of a galaxy that has quite literally blown itself apart in its frenzy to create. Looking at the quiescent aging galaxies that surround us today, it is humbling to realize that many of them, perhaps even our own Milky Way, may have endured such a violent youth. They are the survivors, the galactic elders that have settled into a quiet, predictable middle age. But the starbursts show us the untamed primordial power that still lurks within the cosmos, a reminder that the universe is not a static, placid expanse, but a dynamic, evolving entity still, very much in the throes of its own creation. They are a window into a more violent, more energetic and more formative epoch of cosmic history. By studying them, we're not just observing distant objects, we are piecing together the story of our own cosmic ancestry, tracing the chaotic path that led from a universe of simple gas to a cosmos rich with the potential for planets, complexity, and life. The elements that constitute your very being were forged and distributed by processes identical to the ones we have just witnessed. You're in the most literal sense a child of the starburst, but the influence of these celestial firestorms extends far beyond the confines of their host galaxies. They are not isolated episodes of violence, they are crucial architects of the cosmic landscape shaping the evolution of the universe on the largest possible scales. The very galactic winds that signal the end of the starburst, the ones that starve the galaxy of its fuel, and usher in a long period of quiescence, are also immense distribution networks. They are the universe's couriers carrying a precious cargo of newly forged heavy elements out of the dense galactic core and into the vast empty expanse of intergalactic space. This material, this stellar ash, does not simply dissipate into the void. Instead, it enriches the pristine hydrogen and helium of the cosmic web, that grand filamentary structure upon which galaxies are strung like pearls. Imagine these outflows as colossal seeding machines travelling for millions of years across the cosmic ocean, planting the seeds of future complexity in otherwise barren territory. When this enriched gas is later drawn into the gravitational embrace of a different developing galaxy, it carries with it the potential for a richer, more diverse chemistry. That next generation of stars and planets will form from a medium already seasoned with carbon, oxygen, nitrogen, and iron. This process, known as cosmic enrichment, is absolutely fundamental to the universe we see today. Without the violent sacrificial act of the starburst galaxies, the intergalactic medium would have remained chemically primitive. Subsequent generations of galaxies would have been unable to form rocky planets, and the essential ingredients for life would have remained locked away, forever trapped inside the galaxies where they were first created. Starbursts therefore act as the universe's great equalizers. They prevent the cosmos from becoming a collection of isolated, chemically distinct islands. They ensure that the fruits of stellar alchemy are shared, creating a more homogeneous and interconnected cosmic ecosystem. They are the engines that drive the universe's evolution from a simple, predictable state to one of immense complexity and potential. Furthermore, the immense energy they inject into their surroundings has a profound sculpting effect. The powerful radiation and relativistic particles streaming from a starburst can heat the gas in nearby dwarf galaxies, preventing it from cooling and collapsing to form stars of its own. In this way, a single dominant starburst can regulate the growth of its entire local group, acting as a cosmic thermostat that dictates the pace of star formation across millions of light years. This intricate feedback loop, where the processes within one galaxy can dramatically alter the fate of its neighbours, reveals a universe that is far more interconnected than we ever imagined. The cosmic web is not just a passive scaffold, it is a dynamic circulatory system, and starburst galaxies are its powerful beating hearts, pumping energy and enriched material throughout the entire structure. They are responsible for the distribution of matter and energy that ultimately dictates which galaxies will grow large and luminous and which will remain small and faint. Understanding this grand interplay, this cosmic environmental science, is one of the next great frontiers in astrophysics. We are moving beyond studying galaxies as isolated specimens and beginning to appreciate them as key components in a vast, interconnected and evolving biological system, where the actions of one can have profound consequences for the whole. The story of a single starburst is in reality the story of how an entire cosmic neighbourhood is built. Yet for all that we have learned, for every layer of this cosmic onion we have managed to peel back, we find ourselves confronted with even deeper, more profound mysteries. We have built a compelling narrative of the starburst life cycle, but the precise mechanisms that trigger and sustain it, and the intricate relationship it shares with the monster at its heart, remain tantalizingly obscure. At the center of nearly every massive galaxy, including these starbursts, lurks a supermassive black hole, a gravitational behemoth millions or even billions of times the mass of our Sun. For a long time, we saw these as two separate phenomena, the furious star formation in the galaxy and the dormant monster in the core. We now know this view is profoundly naive. They are locked in a cosmic dance of unimaginable power, a complex feedback loop that likely governs the entire evolution of the galaxy. And we are only just beginning to learn the steps. Is it a symbiotic relationship or a parasitic one? We see evidence for both. The same catastrophic event, like the merger of two galaxies that funnels immense quantities of gas toward the galactic centre, to fuel the starburst also feeds the supermassive black hole. As the black hole consumes this material, it can flare into a quasar object so luminous it can outshine its entire host galaxy. The intense radiation and powerful jets from this active galactic nucleus can then plough into the surrounding gas, compressing it, and potentially triggering even more star formation. In this scenario, the black hole acts as an accomplice, a co-conspirator in the galaxy's creative frenzy. It is the gravitational anchor that helps gather the fuel its own violent accretion process, serving as the spark that helps ignite the galactic fire. But we also see evidence for the exact opposite. Those same powerful jets and winds emanating from the black hole's accretion disk can become too effective. They can heat the gas to such extreme temperatures that it can no longer cool and collapse into stars. They can physically blast the fuel reservoirs out of the galaxy entirely, prematurely quenching the starburst and sterilizing the galaxy for billions of years to come. In this dark narrative, the black hole is not a partner but a predator, a cosmic tyrant that ultimately consumes or expels the very substance that gives its host galaxy life. It waits for the feast to begin, then awakens and single-handedly brings the celebration to a close, ensuring that its own dominance is absolute. Which of these narratives is true? The answer is likely both a delicate and poorly understood balance between positive and negative feedback that shifts over the course of the starburst. Untangling this complex relationship is one of the most pressing challenges in modern astrophysics. The core of a starburst galaxy is one of the most extreme and visually obscured environments in the universe, shrouded in impenetrable veils of dust. Observing the delicate interplay between star formation and black hole accretion within this cauldron is like trying to watch a hummingbird's wings beat in the heart of a hurricane. We are attempting to connect processes that occur on the scale of a solar system, the accretion disk of the black hole, with those that span the entire galaxy. It is a puzzle of immense scale and complexity, a cosmic chicken and egg problem, where it is nearly impossible to tell which came first, the awakening of the black hole or the ignition of the starburst. Solving it will require not just more powerful telescopes, but entirely new ways of thinking about how the largest and smallest structures in the cosmos communicate with one another. And the mysteries do not end at the galactic core. We still grapple with the fundamental question of fuel. We know that major galaxy mergers are a reliable way to trigger a starburst, the gravitational collision, acting like a cosmic snowplow, sweeping vast reserves of gas into a concentrated central pile. But we are finding more and more starburst galaxies that show no obvious signs of a recent violent collision. They appear relatively isolated, yet are still aflame with furious star formation. What is feeding their fire? The answers may lie in more subtle processes that are only now coming into view. Perhaps they are being fed by the cosmic web itself, siphoning cold streams of gas directly from the intergalactic filaments, like a whale feeding on a stream of krill. Or perhaps the trigger is internal, a slow-acting instability within the galaxy's own structure, like the formation of a stellar bar that efficiently funnels gas from the outer disk towards the centre over millions of years. These more clandestine fueling mechanisms are far more difficult to confirm, but they suggest that the universe has more than one way to ignite a galactic firestorm. It doesn't always require the spectacular violence of a head-on collision. Sometimes a slow, steady and persistent gravitational squeeze is all it takes. The quest now is to understand the relative importance of these different triggers across cosmic time. Were the dramatic mergers more common in the early universe, while the more subtle secular processes dominate today? Answering this will provide a complete inventory of the universe's fire starters, giving us a far richer and more nuanced understanding of how galaxies evolve. To pierce these veils and answer these profound questions, we are building new eyes on the cosmos' technological marvels, that will allow us to gaze into the dusty hearts of these celestial factories with unprecedented clarity. The James Webb Space Telescope, with its extraordinary sensitivity to infrared light, is a machine built for this very purpose. Infrared radiation can penetrate the dense dust clouds that hide the youngest, most embedded star clusters from view clouds that are utterly opaque to optical telescopes like Hubble. For the first time, Webb is allowing us to part the curtains on these stellar nurseries and witness the very moment of stellar birth. It is giving us an accurate census of the newborn stars, allowing us to measure the true unobscured star formation rate and see precisely where and how the feedback from these young stars begins to sculpt their environment. Meanwhile, on the ground, arrays of radio telescopes like the Atacama Large Millimeter just Submillimeter Array, or ALMA, are giving us an entirely different but equally crucial perspective. ALMA doesn't see the stars themselves. Instead, it sees the cold, dark molecular gas from which the stars are born. It maps the fuel reservoirs. With ALMA, we can trace the intricate network of gas filaments as they spiral toward the galactic center, measuring their density, temperature, and velocity. We can see the galactic winds not as glowing ionized gas, but as vast outflows of cold molecules being ejected from the galaxy. It is like having a weather map of the starburst showing us where the fuel is located, how it is moving, and how quickly it is being consumed or expelled. By combining the after picture from Webb with the before picture from ALMA, we can finally construct a complete multifaceted view of the entire starburst process from cold fuel to newborn star to galactic outflow. And beyond these incredible observatories, a new generation is on the horizon. The extremely large telescope and the 30-meter telescope will provide images of distant starbursts so sharp they will be able to resolve individual regions of star formation that are currently just blurry smudges of light. The Nancy Grace Roman Space Telescope will survey vast swathes of the sky, discovering thousands upon thousands of these rare galaxies, allowing us to study them not as individual curiosities but as a diverse and varied population. Each new instrument, each new technological leap brings us closer to a complete understanding. We are living in a golden age of discovery where the secrets of these most violent star factories are finally being laid bare. Our journey through the life and death of starburst galaxies is in the end a journey back to ourselves. We have seen that the universe is not a quiet, gentle place. It is a realm of unimaginable violence, of explosive change, and of constant turbulent creation. These galaxies in all their chaotic and ephemeral glory embody this truth. They are the crucibles in which the very substance of our world was forged. The ferocious light of their newborn stars and the cataclysmic shockwaves of their deaths were not acts of senseless destruction, but necessary steps in the universe's long, arduous journey toward complexity. The violence was creative. The chaos was constructive. From this cosmic fire, the possibility of order, of structure of planets, and ultimately of life could emerge. When you look up at the night sky at the serene and silent stars, remember the hidden fury that lies behind that tranquility. Remember the starbursts raging in the distant cosmos tirelessly, performing the alchemy that makes your existence possible. They are a profound testament to the universe's ability to create beauty and meaning out of the most extreme conditions imaginable. The story of the cosmos is written in fire, and in these galaxies we can read its most dramatic, most consequential, and most awe-inspiring chapter. The quest to understand them is far from over. New mysteries will undoubtedly arise. But with each discovery we move one step closer to understanding not only the universe but our own fundamental place within it. For the story of the starburst galaxy is our story writ large in fire and light across the heavens.